Hi, this is Luis, and for our MAE 152 project, we decided to analyze components from a Liebherr 980 excavator. Here are the list of components that were analyzed. We will showcase the studies for the bucket, boom, tread, and hydraulic cylinder. This is the original model of the bucket. So here are the loadings of the buckets. Two different cases were done for the bucket as shown on the right hand side. For case 1, a 10,000 Newton load was applied on the bucket interior, as well as the teeth. For case 2, a 50,000 Newton load was applied on the bucket interior. Both cases have fixed hinges as the boundary conditions. The stress, displacements, as well as the first three modes of vibration are shown for the original model. As you can see, stress exceeds the yield strength of the material, and further iterations will focus on tackling this issue. For the first iteration, 20mm fillets were added to the underside of the teeth. Before, there were sharp edges that produced a high amount of stress. Once the fillets were added, the max stress was reduced by around 70 megapascals for the first case. Unfortunately, the displacements changed very little in both cases 1 and 2, and the stresses are still above the yield point of the material. The next iteration will focus on reducing the displacements and stresses even further. For the second iteration, the thickness of the bucket rim was increased from 30mm to 50mm in an attempt to increase the stiffness of the overall structure. Increasing the thickness proved to be very successful, as both max stress and max displacements were reduced tremendously. The only issue that occurs is that modes 1 and 2 are close to the natural frequencies of the engine at max torque and max horsepower, which are 21.6 Hz and 30 Hz respectively. A modal analysis of the whole arm assembly and bucket would need to be done to further test for these problematic frequencies. Lastly, this slide summarizes the max stress, max displacement, and natural frequencies for all three iterations.
Next is the analysis of the boom arm pictured here. All of the simulations utilize alloy steel. There are three different simulations that will be covered. Case 1, a linear static analysis with a 75 kN load applied to the connection, a thermal stress from 30 to 110 Fahrenheit, and two fixed hinge boundary conditions. Case 2 is the same except the load is applied at the bucket position, and Case 3 is a modal analysis. The original model resulted in 213.6 megapascals, a max displacement of 1.694 mm, and a resonant frequency of 2940 RPM. The first iteration has filled some edges and reduced stress by 14%, displacement by 13%, and no change to resonance. And the second iteration was the same or marginally worse in all categories.
Alright, hello, my name is Colin Brown, and I'll be presenting on the undercarriage tread. So the material is cast alloy steel, and the mesh is the finest mesh setting on the setting slider for blended curvature. For static on terrain, the boundary conditions are supported on the ground and in the internal faces with loads of 1,000 kilonewtons of downward force as well as 10,000 kilonewtons of torque force. So here are the stress and displacement plots. Also, modal analysis has been performed, and the frequencies do not match, fortunately, the engine's equivalent 30 Hz rating. For the third case, thermal effects, there are no boundary conditions, but miscellaneous thermal loads have been applied to simulate thermal effects in real time. For iteration, I've done fillets and thicker treads by 100 millimeters for the thicker tread. For fatigue analysis, I have performed a life cycle plot that is based on known SN curve values for cast alloy steel, and here is the life cycle plot. Here is the SN curve, and with the intersection at about 75,000 cycles and 135,000 psi, this can go. For case 5, I have performed a linear analysis once again, this time with thermal simulations involved, as well as the two design iterations.
For the hydraulic cylinder, the material was alloy steel, and all simulations were run with the medium mesh size. The first case is a linear static analysis with the green arrow showing fixed boundary conditions and a 50,000 Newton force downwards. The max stress is 8.37 megapascals, and the yield strength of alloy steel is 6.2, so the part does not fail from static loading. The second case is modal analysis, where the boundary conditions are the same as in the previous. The resonant frequency of the engine is 30 Hz, which from the table we can see we avoid, so there should be no issues. The third case is buckling, where the inner circular face is fixed and there's a 50,000 Newton force downwards. In the original case, there is no failure. However, I increased and decreased the wall thickness to see how that would affect the buckling factor of safety. In all cases, we still meet the requirement. However, the 5mm one is recommended since it still meets the requirements and uses less material. However, the fluids part of the cylinder is not modeled, which can affect these results. Lastly, a closed solution was performed by comparing the FEA results to hand calculations. The hand calculations are on the right, and as we could see, there's a 16.7% error. However, this is probably due to a lot of rounding